Here I gave you that rate of change question, rate of change curve, and I ask you which one of these is an approximate rate of change function for intervals of 0.5 seconds using the left approach. For 0 to 2, first 2 seconds. So these first two on the left are not showing an approximate function. They're showing something else. They're showing rectangles. So in terms of approximate functions, it's going to be one of these four. And if we're using the left approach, that's either B or E. And then, so E would be the right one. Yeah, thank you. Yes, wait, thank you. Okay, so this is the approximate rate function. For a left approach, we're using the rates at the left side of each interval. And we don't want this one because this actually goes out to 2.5. And we just want the first 2 seconds. So this goes out to 2.5, so that one's not right. So we want E. Okay, E is the answer to this question. And so what is this about? So we said that we're going to total up the total amount of change by looking at little amounts of change, right? So we're going to sum up. So we would take, so this is what, F of 0 here, and then, so if we take the rate in the first interval times dx, right? Rate times dx, plus the rate in the second interval, which we get from f of 0.5, times dx, plus the rate we get in the third interval, times dx, plus the rate from the fourth interval. It's the left-hand side is at 1.5, so we take the rate at 1.5 for the whole interval, times 0.5. And this approximates the total amount of change from 0 to 2. And so what we said was we could use summation notation to kind of summarize that. We say the sum Sj goes from 1 to 4. F of, say, xj delta x. So we said this summation notation was the approximate amount of change in the first 2 seconds. So what are we doing? We're summing up rate times delta x plus rate times delta x plus rate times delta x, and that gave us an approximate. How do we get that exact amount of change? How do we get that exact amount of change? So this is a way to get an approximate amount of change. How do we get the exact amount of change from 0 to 2? Should all be thinking what? Integral, right? So this, when our interval gets very small, that notation right there, sum becomes sum. F dx, right? From, this is what we just talked about. So this is exact amount of change. Okay? So now if we look what's going on here, there's another way to look at this. Okay, so that's review. That's review. This is a focus of accumulation and rate of change way of looking at integral. And that's how what we've really emphasized so far. Looking at an integral in terms of rate of change and amount of change or amount of accumulation. But if we come here to the graph and look, we see that, say, for right here, that 0.5 is like this distance right here. So I'm looking at this right here. The third interval, okay? The third interval. What is that? How is F1 represented on the graph? F1 is represented by this length right there. The y-coordinate is the vertical distance, right? And so what we see is this 0.5 times F1 is like this length times this length. And what do you get when you do that length times that length? Yeah, so it could represent the area of a rectangle. Okay? The area of a rectangle, where 0.5 is the width of your base, and f of 1 is your height. Okay? But this is only because of the way that we graph things. It's like a coincidence. It's not the true meaning like rate of change is. It's just because we graph at right angles, it happens to be that. It's kind of incidentally. Incidentally, we could see this kind of as a geometric figure, as the area of a rectangle. Okay? But that's only because of the way that we choose to graph things at right angles to each other. Okay? This way is our change in x, and this way is our value of our function. Okay? So it's not a deep meaning the way that we want to focus on rate of change. It's just kind of incidentally we get this geometric result that each one of these is the area of a rectangle. Could be viewed as that view of things, an area of rectangles view of things, leads us to what? Choice A or choice D? You see what it would be? A or D? A. So if we wanted to look at that total amount of change, but instead look at it as a sum of areas of rectangles, that would lead us to choice A. But it's not. That's no longer about an approximate rate function, right? That's about geometry. So a geometric perspective to this summing up bits of change is summing up areas of rectangles. Geometric perspective on summing up bits of change is summing up areas of rectangles. Okay? And what kind of curve would that be for what we emphasize? Is that an amount function or a rate function? Amount or rate for our old perspective? No, rate. This is the original rate function, and we're approximating it with approximate rate, with the horizontal constant rates of change. From a geometric perspective, we remember that, that was a rate curve. But now it could be anything, if we're just talking about area. Okay? But we remember, in our perspective, that curve was a rate of change. Was rate of change. When we move in geometry, it's like, okay, well, it could be anything. We're just talking about area on the graph. Okay, so that's where we're going now. So we're going to leave the land of the more significant to the land of geometry, which is important, but it's not a deep principle the way that rate of change and accumulation is. So let's talk about, let's see if I still have this here. Somewhere, do I have it? Did I lose my... All right, so here's kind of a reboot of that same question. All right, so that looks about the same. Our red curve was our rate curve from before, and now we're looking at it in terms of rectangles as before. So we know that when we chunked it up into intervals, we got an approximate amount of change, not the real amount of change. So, and to get the real amount of change, what do? We made the intervals smaller. So in the geometric perspective, what happens when we make the intervals smaller? So it's like, instead of adding up amounts of change, now we're adding up areas of rectangles. And if we're to take more rectangles, so here's kind of the situation that was on your exam, then I'm going to go up, say, to 20. So now for that same 0 to 2, you're adding up the areas of those rectangles. Before it was adding up amounts of change, now we're adding up areas of rectangles. What are we, as we divide it up more and more and get thinner and thinner rectangles, so I'll go up to 50. What is the sum of those rectangles, the sum of the areas of those rectangles converging on? So it's like, isn't it the tops of those rectangles are doing a better job of mimicking the curve? And so if we're adding up all those areas of those rectangles, it's like we're adding up. So here's even more rectangles. By adding up those rectangles, it's like we're adding up the total area between the curve and the x-axis. So before, we added up chunks of change, and we got an approximate total amount of change. With a geometric perspective, we add up rectangles, we get an approximate to that area under the curve. And as we take lots and lots of rectangles that are skinnier and skinnier, we converge on the actual area under the curve in the geometric perspective. Okay, so it's like we're doing sum of base times height. Base being our delta x, height being our function values. And when we take more and more rectangles of narrower width, it converges to our integral. So in this case, from 0 to 2. So our new perspective is area under the curve, or area between the curve and the x-axis. So the summation is the approximate area, because we got those chunky rectangles that are not getting the area exactly, and then our integral is exact area. Okay, and that may be more familiar to what you saw before, because it's kind of this geometry has kind of hijacked calculus in the United States over the last 50 years. It's become all about area, and we've lost the real profound meaning of rate of change and accumulation. Everything is taught by area. So I looked I think in your textbook, the section on the fundamental theorem of calculus has nothing to do with rate of change. It's all about this just areas, okay? Which is important for some things in geometry, but it's not. It doesn't have the meaning and the significance that the rate of change perspective does. Okay. All right. So let's. Where we at? Okay. So we're talking about integral as area. Okay, and we say it's not as deep a principle as integral as accumulation of a quantity, but still important for geometric purposes. Still important. Okay? So how can we find the area bounded by y equals 5x minus x squared in the x-axis? Well, the first thing about that is that we need to know how to sketch this. Okay? So for easy functions like this, hopefully you can sketch it without your graphing calculator. Ones that get a little more complicated, your graphing calculator will be fine. But pictures are going to be huge in this. This is geometry. You need visuals, okay? So one way to sketch this without a graphing calculator is factor it, x times 5 minus x. That can help us, right? What does that immediately tell us about the graph of this function? What do we know immediately? If we have x times 5 minus x. It's not on your smartphone. It's positive. Well, it can be positive or negative. Why did I factor that? How did that help me get started? Roots, right? Roots. What are the roots? 0. If x equals 0, y equals 0. And if x equals 5, y equals 0. From this, if you remember your quadratics, we got minus x squared. So does it open up or down? It opens down. So if we got a parabola, x squared, it opens down, and it has these roots. It's got to look like, can you imagine what it has to look like now? So that's the kind of reasoning you want to do for these simple graphs. You don't want to have to depend on the graphing calculator for simple ones like this. But it's got to look something like this. So now we can make sense. What area is it talking about? The area bounded, should have said area of the region. Area of the region bounded by our curve and the x-axis. Can you see what area it's talking about? You should imagine this right here. Okay, so here's this technique that I want to show you, and I'm going to beg of you to do. I'm going to plead with you. And still, most of you are going to be like, I don't need to do that. I'll just do it my way. Okay, but when it gets harder, we start talking about volumes, okay, and we start talking about these physics applications. What I'm about to show you is going to be very crucial to help you. So, again, I'm begging you, I'm pleading with you to look at this. So what did we say? Look at it this way. So what did we say about getting this area? It's based on rectangles, right? So we're going to draw a typical rectangle, but it's just going to be really thin. We know that the really thin is going to give us, it's still not on your smartphone. It's still not on your smartphone. Let me just put it away. Okay? So we're still going to think about rectangles, but really thin ones. The really thin ones, when added up, give us the exact area. So what we're going to do is we're going to do what's called instead of rectangle, because they're really thin, we're going to call it a typical strip. We're going to draw a typical strip, okay? And so what is that? It's a really thin rectangle that has, that's going to be like all of them, all the way across like this. So that's our typical strip. And what do we want? We want the area of a typical strip. And then we're going to add them all up, add up all the typical strips. So our area of a typical strip is, it's like a rectangle, so it's base times height. Okay, so I'm going to draw it again over here. What's the base? What is the base of our typical strip based on what we talked about earlier? Delta x, right? So when we do the typical strip, think of it as finite. It actually has width. It has some width, delta x. And then what's the height of that typical strip? The height is what? Yeah, it's going to be whatever the value of the function is at the x value that we chose, right? So if this is x, so this is actually, I didn't make a function, so this is just actually y. That's the height, it's y. The height of that typical strip is y. So the area of the typical strip is base times height, or y times delta x. Just switch the order, okay? But if it's delta x, then we need everything in terms of x. So what is y in terms of x? What is y in terms of x? 5x minus x squared. That's how y is defined for this curve. So this is the area, we'll say A sub s. That's the area of our typical strip. Okay, we're doing this because for harder examples in the next 3 or 4 weeks, this is going to be an important technique that you all should have. So this is our setup. This is our setup. And so then how do we get the total area? We get the total area by adding up all the typical strips, starting at where? So our first typical strip is over here. And our last typical strip is at what? So you've got, think of a zillion. You've got a zillion typical strips that are really thin. The first one is at x equals 0. The last one is at x equals 5. And so that the area that we want is, we're going to sum up all the typical strips, okay, that are really, really thin, starting at x equals 0, ending at 5. Please practice this, okay? Don't bypass this. Practice this. I'm telling you, when things get harder with volumes and physics applications, this habit is going to be really helpful. Okay, so then this is super easy, right? All right, I just want to talk about one more thing. Real fast, all right? So in whatever the value of that integral is now, in the geometric perspective, is the area of that shaded region, found by adding up all these typical strips, really thin rectangles, starting at 0, ending at 5. Okay, so what about if it was from 0 to 8? Same one. Same integral from 0 to 8. So let's look at the graph. So here's that graph, all of it. So 0 to 8 now starts here and ends at 8. So from the rate of change perspective, the accumulation perspective, what's happening to the quantity here from 0 to 5? Increasing, positive rate. What happens to the quantity here? Starts decreasing because the rate is negative. So this integral from 0 to 8 if it calculates total change in a rate of change perspective, it calculates total change. Then it's going to, from 0 to 5, it's going to, the amount is going to go up. But then as it keeps going from 5 to 8, that amount's going to go back down again, right? It's going to subtract off the amount that you lose at the negative rate. So if in the geometric perspective, what's going to happen? It's going to do the same thing in the geometric perspective. We're going to add up all these typical strips. Our area is going to increase. But then what's going to happen now? Yeah, so this, if this is A2 and this is A1, in terms of A2 and A1, what does it equal? A1 plus A2? No, it's going to be A1 minus A2 because, so think of it from the rate of change perspective. Where the rate is negative, the amount's going to go down. So from the area perspective, where that curve is below the x-axis, you're going to have a reduction in whatever total area. So it would be A1 minus A2. So to say the integral area is not quite precise enough. Integral gives difference of areas. Whenever that function goes underneath the curve, those areas that are carved out get subtracted out of the total. So if we wanted the total area, what would we have to do? If we wanted the total area, A1 plus 2, we'd have to split this up and go from 0 to 5, that first one we did. And then plus the opposite of 5 to 8. Because that integral will be negative. And if we take the opposite of it, we'll get the true area A2. We can add them together. That would give the total area. But just the single integral will always subtract off areas that are created below the x-axis. You'll get a difference of areas for a single integral whenever that function goes below.